we saw that pattern matching with suffix tries is fast, but impractical with respect to the memory footprint. How about this idea? We saw that bananas takes a lot of edges in our suffix try. Can we compress all these edges into a single edge? That's very easy to do. So let's simply do this and do it with every non-branching pass in our suffix try. Very quickly, our try gets much smaller, right? So we're almost done. Continue, continue, and finally we construct something that is called suffix tree of text. And since each suffix adds one leaf and at most one internal vertex to the suffix tree, then the number of vertices in the suffix tree is less than 2 times text. And therefore, memory footprint of the suffix tree, which is proportional to the number of edges in the suffix tree, is simply all the length of the text. This sounds like cheating, because we haven't answered the question, how do we store all the edge labels? They will take the same total length of pattern space that all labels in the suffix try took. However, let's try to do the following. So instead of storing the whole string bananas as a label of our edge, let's notice that bananas start at the position 6 of the text and has length 8. And therefore, instead of storing bananas on the edge, we will only store 2 numbers, 6, the starting position of bananas, and 8, the length of bananas. That will be sufficient to reconstruct the entire label bananas. And we'll do it for all edge labels, and as a result, now you see that suffix tree is indeed a very memory efficient way to code all information about suffixes of the text. You may be wondering, why did we add this silly $sign to Panama bananas? I added it because I wanted to make sure that each suffix corresponds to a leaf. But why do we want to make sure that each suffix corresponds to a leaf? I suggest you try to construct suffix tree for papa without adding the $sign and compare it with the suffix tree for papa with $sign, and you will see why the $sign is important. We saw that suffix trees are fast and memory efficient way to do pattern matching. However, construction of suffix trees is not for faint-hearted, because we need to combine all suffixes of the text into a suffix tree, and the naive algorithm for doing this takes quadratic O of text squared time. However, there is an ingenious linear time algorithm for constructing suffix trees called Weiner algorithm, and it was developed over 40 years ago. And this algorithm amazingly has linear write time O of text to construct the suffix tree. So it looks like we are done, finally, after all the efforts. And now I want to tell you about the big secret of the big O notation, something that Sasha, Daniel, Misha, and Neil forgot to tell you about. Indeed, suffix trees enable fast, exact multiply pattern matching with runtime O of text plus patterns and memory O of text. That's the best we can hope for. However, big O notation hides constant, and the best known implementation of suffix tree has large memory footprints of 20 times text, which is a very large memory requirement for long genomes like human genome. But even more importantly, we want to find mutations, and it is not clear how to develop fast approximate multiply pattern matching algorithm using suffix tree. So once again, we are facing an open problem that we have to solve.